Record. Okay, so welcome to the class. We continue with logic and quantified expressions. A little bit of review. That's where we were last time. So we introduced existential quantifier, right? So if T is a proposition, T of X, then this is read there exists X which satisfies this proposition over some domain. And we have a universal quantifier, excuse me, that says for all X in a given domain, the predicate T of X is satisfied. Okay, and we also said that for finite sets, an existential quantifier is like a one big disjunction to say that there exists an element for which that the predicate holds for some element. Another way to read this is that T of X holds for some X. So that means if the domain is finite, that the T holds for one of these, maybe more, right? Because this junction is not exclusive. But it says that at least for one. And conversely, universal quantifier for a finite domain or enumeratable domain is that T holds for all of these. So it could be expressed as a conjunction, right? So we looked at some examples where there is very tricky, the tricky ones, there are some, okay, it gets trickier, like when you start evaluating this, like for example, this one was a tricky one. I mean, in a sense, is it true that is the following statement true for all positive integers? The moment an integer is negative implies that the negative is prime. And it is true because over this domain, the hypothesis is never met. So this is the statement of the form from P to Q. P implies Q, where P part is not true, ever. So therefore, the implication is actually always true. Okay, so that's the kind of tricky stuff that you should avoid saying ever and stating facts in that way. But it is okay for us to test you on understanding these, because it basically means what you understand, what an implication is, and what a quantifiers are. So this we didn't get to last time, so that's it for the review. De Morgan's laws for quantified expressions. What happens if I negate existential quantified expression? So I say it's not true that there exists X which satisfies predicate P. Well, it is the same as to say that for all X's, predicate P at X is false, right? And you can say that basically, look, this is just two ways of saying the same thing, which is to say that predicate P never holds. P of X is always false, no matter what X is in the domain. So look, this is, you can say basically in two ways. You can say it. What does it mean that P of X is never satisfied? That there is no argument which makes this statement, whatever it is, true. Okay. Well, one way to say it is that it's not true that there exists some argument that satisfies it. Another way to say it is that for all arguments, it is the case that the argument fails this proposition. The proposition with this argument is false. It is the same thing. It's two ways of seeing the same things. And you can actually see it. It's nothing new, so to speak, because if you think of enumeratable domains, then an existential quantified expression is nothing else but implicitly it is the big disjunction of what does it mean that there exists X which satisfies Px? It means that P is satisfied at V1 or at V2 or at V3. At one of these guys, it is satisfied. And to say that this is not true is to negate this disjunction. And now by standard De Morgan law, you know that when you say it's not true that some disjunction holds, well, the only way to satisfy that is that when is disjunction not true? The only place is that all of these guys are false. That's the only way disjunction ends up evaluating to false. So to state that this disjunction is false is to state that all of these guys are false, which is this, right? So that's the standard De Morgan law. And now I can express this using a universal quantifier, because what is the big conjunction of not true at P is not true at V1 and P is not true at V2. So basically the not P proposition is holds for all X. Yeah, or otherwise P is false for all X. So this is basically the standard De Morgan in disguise, right? There is the other De Morgan is what happens when you negate a conjunction, and that corresponds to negating a universal quantifier. Because what does the left-hand side say? It says, well, what does this statement say? It says that predicate P holds for all arguments. And this one says that it is not true that predicate P holds for all arguments. What does it mean that when I say it's not true that some predicate holds for all arguments? Well, then it means that I have some counterexample, right? Like it's this statement can only be true if there is some counterexample, right? Like otherwise, it is true that P of X is satisfied for all X's, right? So another way to say the same thing is that there exists a counterexample. So there exists an X which falsifies this predicate, right? And it is if and only if. They really are saying the same thing. And again, the way to, hold on a second, I think that the noise from outside is going to be disruptive. So hold on. Sorry about that. So it is a standard De Morgan in disguise, because there exists X, sorry, for all X, Px is nothing but a big conjunction that says that predicate P holds on all arguments in the domain. And to negate that is to say that it either does not hold on the first or not on the second, and so forth. It's a disjunction of negations. And once I look at this big disjunction and I identify not P as a predicate, right? Because whatever P is, not P is also a predicate. So I can say this. I can express this whole thing. I can recognize it as there exists an X which makes this predicate, this not P predicate, true. Okay. So let's some simple laws of on quantified expressions. So the first law is like a sort of look, like this has to be true, right? If it is the case that for all X, Px, in other words, predicate P is satisfied for all X's in the domain, then in particular it is true that there exists an argument that satisfies the predicate. All right. If something is true for all arguments, then there exist arguments which make it true. All right. And another law is that if it is false that there exists an X, that satisfies some predicate, then it is therefore false that all x's satisfy a predicate. Now, you might read up, or you might recognize that I didn't say anything different in these two statements. In fact, they are one and the same thing. And look, first of all, you know by counterpositives that anything of the form P implies Q, where P is this expression, Q is this one, can be restated equivalently as not Q implies not P, and that's this one, right? So I just take the consequent in the implication, I negate it, and I make it imply negation of the hypothesis. And these two statements are equivalent because this P implies Q and not Q implies not P is equivalent for any P and Q. In this example, this was my little p, and this was my little q. You can also look at this as follows. You can use the Morgan's law to derive it as well. So what is, let's see that this guy implies this guy. So this thing is not, it's not true that there exists an x which satisfies predicate p. Well, by the Morgan law, that is the same thing to say, it's equivalent to saying that for all x's, they falsify, every x falsifies predicate p. And now I can use this law, but just apply it to a new predicate, which is p prime, which is not p, right? I did this in the previous slides as well, right? So just think of this not p as a predicate and run this law. So now that you say that for all x's, not p of x, that implies that there exists x such that not p of x. And now just envelope it by using the Morgan law again, and this is equivalent to that, right? So the same thing you can see in two different ways, probably even in more. One thing also to take from this the De Morgan law is that if you have a statement which has negation over some quantifier, then you can, this is for some reason easier for you to think through what that means. You can push this negation inside of the quantified expression, but if you push it, the quantifier sign changes. It flips from there exists to for all. And what? You have a negation of some quantified expression, starting with the universal quantifier, pushing the negation side towards the expression, resulted in the flip of the quantifier sign. These, basically, if you have a big expression with a bunch of quantifiers in first, you can push the negation closer to the statement if you so wish. You just have to flip the quantifiers. Okay. Let's look at some examples of quantified statements. So here's two that occur very often in the wild, right? Like these are the kind of commonly things that you might find yourself saying, and you might find other people saying, and they are convenient and commonly occurring, right? So for example, you say you have some two predicates, P and Q. Okay, let's say that these are predicates, these express some conditions on input to a code. Okay, that the inputs have to have meet some formatting requirements, and also they have to be within some range, numerical range or okay, what have you. These are two conditions. And you say that there exists some input that satisfies both conditions. Okay, natural enough, right? Here is another one. I mean, you can also, it's also natural to have, you know, for there exists an X such that would satisfy either of the two conditions, right? So a lot of stuff is natural, but this is an example. Here's another example. I want to say, what does this say? It says that for every X, if the first condition is satisfied on X, then necessarily the second condition will be. This is also commonly useful, right? Like I want to, reason that, you know, if for every axis, if they, you know, if they satisfy some criteria of some, you know, program, then they will also satisfy a criteria of the other code, right? Like, you know, this is a code upgrade, and it's like you need to say everything that was done by the previous one will also be handled by the new one. Okay, and you want to say a quick criterion for this to express that.
I've got a quick question.
Oh yeah. Sorry, I have my volume badly set up.
Yeah, sorry. So what were to happen if you were to use a conditional on the existential statement or on the universal statement?
Very weird stuff.
Did we go over an example for each or something?
Yeah. So I had like examples of standard stuff and examples of weird stuff. Let's see how far we got. I forgot right now whether I have it or I think so. Okay. Perhaps even here. I just don't remember right now. But yes. That's like these are the kind of weird expressions that you take a pause to evaluate. We had an example 2 slides back. Okay. So but first I want to point out that this can be stated in slightly different syntax, and you should be familiar with that syntax as well. So what this says is that for all x's which, if they satisfy this predicate, then they satisfy that one, right? So you can say it using this way, instead of saying for all elements in some domain, in some huge domain, basically P of X is like you can think of it as identifying a subdomain, only those X's that satisfy P. And what you're saying is that for those X's that satisfy P, it will also necessarily follow that they will satisfy Q. So I can explicitly say this in the form of a domain. For all X's ranging of the domain of those that satisfy the P, I'm just saying for all X's in this domain, Q will hold on them. They will also satisfy predicate Q. Okay, this is a different syntax, but that's how this thing can be read that way and vice versa, right? So you can recognize these implications as restricting the domain. Notice both this statement and this statement essentially say nothing about X's which do not satisfy P. In what sense they say nothing? Well, they don't say whether they satisfy Q. Maybe some of those that don't satisfy P satisfy Q. Maybe some of those that don't satisfy P don't satisfy Q. It says nothing about them. Why? Because everyone who doesn't satisfy P will make this implication true, regardless of whether they satisfy Q or not. Likewise, this thing explicitly says that the statement should be read only for X's that satisfy Px. And it says nothing about X's that don't satisfy, right? In a sense, this is easier to read because this basically makes this point explicitly, so that nobody can read this and think like, oh, what about X's that don't satisfy P? Well, clearly we said nothing about them. Okay, but it's also true here if you remember that implication will always hold if the hypothesis is false. Okay, so here is, oh yeah, that's an example of the one that I think the students exactly said that. Here is a natural kind of statement. Of course, it can be said, right? It's just that sort of infrequent cases where you would want to say something like this, except to be tricky and to test understanding of logic. So Siemens says there exists an X for which the implication is true. Okay, unlike this one where I universally quantify the implication, here I say I existentially quantify it. Now, here is one way to quickly see what happens here. Rewrite an implication as disjunction of negation of the hypothesis and a consequent, right? So we know that to say that P of X implies Q of X is equivalent to saying either P of X is false or Q of X is true. So in other words, this statement now is this one. It is somebody who said this basically said that there exists an X which either falsifies P or satisfies Q. Now, in this form, it makes sense. You know, perhaps this is some constraint, and there is another constraint, and you want to say that there is an existent element which falsifies the first constraint, but satisfies the second. Okay, that there is an X which does either one. Okay, sorry, it's either one. So this is an honest form, right? Like you can read this easily. There exists an X which either falsifies P or satisfies Q. Okay, we all know how to read this. This statement is equivalent, but it's kind of tricky. Like when you stare at this, you might make a mistake until you recognize that these two are equivalent. And now this one, I think, for the human mind is just easier to process. Okay. Now you can say, what does it mean to say, yeah, but you see, like if I do, for example, if I switch this with the universal quantifier, I don't have such a, you know, it's not tricky to say for all X, two constraints hold. There's nothing tricky really about that. Okay. Moreover, all of these things can be said. It's just that some of them are like, what? Okay. You can, okay, nested quantifiers. Okay, so we can combine quantified expressions and build larger and larger quantified expressions. Let's take it slow and sort of work through how this nested quantification works. I will spend some time on it. I think that nested quantification does give, you know, it's like it takes time to wrap around, and it's useful to see some examples, maybe at a slow pace. Okay. So the basic thing is that you can quantify variables in any expression as long as they are free in that expression, and that expression can be quantified itself. Okay, so let's look at an example of a predicate on two variables, which I would define to be T of xy holds if y is twice x. Okay, so I call it T. Like I will read it. T of xy is that y is twice x. So for example, T of 1, 2 is true because 2 is twice 1, but T of 1, 3 is not true. 3 is not twice 1. Okay. Now define a sort of second level predicate. Predicate on just variable P, y is that there exists an x such that twice x is y. That this formula, this predicate holds on the pair, right? Which, like in this context, this pair is, this predicate is, you can read it, twice x is y. Okay, so this is defined over integers. Let's say integers is our implicit domain here. So now let's look at this predicate. What does it mean to say about a number y that there exists an x such that twice x is that number? Okay, so is P of 2 true? Yes, it is, because there exists an x such that twice x is 2. What is that x? It is only 1. It's 1. But it exists in this domain. Now, P of 3 is false, because if I instantiate with 3, then this says there exists an x such that twice x is 3. Y is 3. And that statement is false. There is no x such that twice x is 3 over the domain of integers, right? So in reals or rationals, it does exist. It's 3 halves, right? 1.5. But over integers, it doesn't exist. Over integers, it is true that all x's falsify this. And therefore, it is not true. So, right? So if all x's falsify, then it is not true that there exists an x, right? So this is the De Morgan law. So therefore, P of 3 is false. Okay. Anyone who can tell me how you can read this? What does it mean to say that P holds about y? Say it fast. Like what kind of y's would satisfy this? What y's are such that there exists a number which twice that number is y? It's a known property of an integer. Chat, even, good, yes, yeah, thank you, yeah, exactly. And maybe, sometimes and very often, or maybe always, sort of an intuitive understanding of what this predicate says is very helpful, because it's like, what does it mean that there exists x such as twice x is y? It means exactly y is even. And so this statement simply says 2 is even. And this statement simply says 3 is even, and therefore it's a false statement. Okay. So now look at the quantified expressions involving this predicate. And now we know that this predicate says y is even. So let's look at this predicate. There exists quantified expression. There exists an y which such that P of y. But since P of y means that y is even, the statement there exists an even number is true. And we already know that, well, yes. So 2 is an example, 4, 6, any even number is an example. What about there exists is for all y, P of y. So for all y is even. So all integers are even. Well, that's clearly false, and we already see it. Excuse me. Now, nested quantifiers are nothing else than this type of thing. So it's a quantified expression which itself is quantified. So because basically to say a number is even actually is a quantified expression. To say that the number is even is to say that there exists a divisor such that twice the divisor is that number, right? So I implicitly basically define like the notion of what it means for a number to be even is that there exists a divisor, and one of that is 2 and something forms the number, right? But sometimes I don't think that a predicate is really a quantified expression. So if I envelop P of y as it's in its full quantified expression glory, as there exists x such that T of xy, then I will rewrite this statement like as follows: there exists y such that there exists x that twice x is y, and this statement is for all y there exists x that twice x is y. Okay, And conversely, if you see a big quantifier, I mean, a series of quantifiers, you can put brackets and think of the inside expression as some predicate, in this case on y. And the whole thing is asking, does there exist in y, such that whatever this predicate, this inner predicate, inner quantified expression, if you think of this as predicate on y, is this true or not? Okay. The immediate question that might occur to you is, what about the order of these quantifiers? Is it like, is this expression, can I reorder them if it's somehow convenient for me to think? Sometimes, but sometimes not, and you will see examples. Okay, let's look at just another an example with the different inner predicates. So now the predicate is x is smaller than y, and I change my domain to positive integers. So all of this stuff is very, very sensitive to domain, right? Because this statement is over rationals true about every x, about every y. Every y is divisible by 2. Every rational is divisible by 2. That's what this thing says. So there exists a rational that is divisible by 2? Yes. All rationals are divisible by 2? Yes. So the domain is, these statements are very sensitive to what is the domain. Likewise, this, you have to pay close attention to what the domain is. Okay, so let's see. First of all, if I have some expression that involves a bunch of variables, to evaluate whether the expression is true or false, I have to instantiate all the variables. Otherwise, I cannot evaluate. But I can evaluate truth or false of expressions which are fully quantified. In other words, each of the three variables, for each of the three variables participating here, there is some quantifier at some point going, from right to left. No matter what these quantifiers are, as long as all of these variables are quantified, then this expression will be true or false. Perhaps it will be extremely hard to evaluate whether they are, right? So there are hypotheses in mathematics that say that some laws are true for all integers, groups, so forth, and nobody knows whether it is true or false because nobody can prove it, right? These are outstanding hypotheses, and we, struggle with this kind of stuff all the time, where perhaps it's not easy to say, but it is either true or false, nevertheless, right? All right. So here, these are all bound. And now, by the way, what is the truth of this quantified expression? It says there exists an x such that for all y, x is smaller than y. In other words, there exists an x such that all y's are bigger than x. In other words, there exists an x such that all elements in the domain are strictly larger than x. And now this is patently false, right? What is the counterexample that shows you what do you want to, perhaps you want to falsify it, okay? So I will falsify it. How do I falsify a statement that starts with an existential quantifier? I have to show that this inside stuff is false for every x. Then there's no x that makes this true. Okay, so fix an x, take any x, and I'm going to show you this is not true that all y's are greater than it. That's easy to have a counterexample. Take y equal x. It will for sure make this false, right? Because y equal x will be a counterexample for that x. So the inner thing is false for every x, and therefore the whole thing is false. Okay. Now let's flip the quantifiers and see what happens. Is it true that for all y's, there exists an x which is smaller than y. Now, this is a different statement because, if I want to, let's say I want to argue that it's not true and use the same kind of reasoning as before. So let's take a y and examine, is there an x which is smaller than y? Okay, y itself is wrong, but that doesn't mean that there exists some other x, right? So how about y minus 1? Y minus x equal to y minus 1 will satisfy this. So therefore, perhaps this is true for all y. Well, look at the domain. All elements, if y is 3, then there exists y minus 1, 2 in the domain. If y is 2, there exists. But for 1 and 1 y only, this will not work. The smallest y. Yes. So look, this smallest y is going to falsify this, because if you instantiate this quantified expression with the smallest y, then this will falsify this expression. It will not be true that there exists anything that is smaller than the smallest element in the domain. Okay. They were both false, but they had different reasoning why they were, right? So it's basically flipping these signs will actually significantly change what you're saying, right? Okay, what about this kind of expression? There exists an x which is smaller than y. I cannot evaluate truth or falsity because y is not bound. It's a free variable. On the other hand, this is a predicate on y. It's a predicate on y, which, like, once I instantiate, this is a function of y, this expression. For different y's, it's going to be either true or false. So it's a predicate on y. Likewise, this is a predicate on x. X is not bound here. If I don't know what x is, I cannot evaluate this, but it's a predicate on x. So if I, for example, put some quantifier in front on x, there exists x for all x, it will be evaluate, it will be a true or false, right? Because it will be true, fully quantified expression.
Professor? For the second statement, would it be true if we had an infinite domain?
This one, there exists. This one?
No.
This one.
Yeah.
No, well, this is infinite.
Yeah.
So no. So like,
sorry.
Yeah, so basically, if you crossed out positive,
yeah,
right? If it were just
I mean.
integers, then yeah, it would be then true. For every y, there exists an x which is smaller. Take y minus 1, and for every integer, there is an integer, not positive integer, but an integer. Yeah, exactly. So incredibly, So if I just change the domain to all integers, this will be, actually, if I change it to negative integers, it will also be true. For all negative integers, there exists even smaller one. Okay, but this will be false on that domain as well, right? Because this says that, yeah, that there exists a point which is everybody else is bigger. All right. So let me go over this slide because it's like okay. Nested okay, so let's continue with our expression predicate. That is, g of xy is that twice x is y. Okay, and the domain is integers now, not just positive integers, but all of them. So consider nested expressions like this. There exists an y such that there exists an x such that twice xy, or for all y there exists an x such that twice xy. Well, we've seen these. I can think of this inner expression here as the predicate on y. This thing is a predicate on y that says there exists an x which is twice of x makes y, like this. And basically, it's, as we have seen, it's the same as to say that y is twice some other integer. That means y is even. So therefore, now I can evaluate these. This thing means that there exists an y which is even, so it's obviously true. For all y is even, it's not true. Okay, let's do some other examples. What happens if I switch the order here? Oh no, sorry, I don't switch the order. Instead of, but my inner expression is for all x, g of xy. So there exists a y such that for all x, twice x make a y. For all y, for all x, twice x make a y. Okay, let's look at this inner. Think of what the inner thing says as a predicate on y. I'm going to define it as the Q predicate on y. The predicate says for all x, twice x is y. Well, is this ever true on any y? This is kind of a strange predicate. It says about some number y that it is the case that that number y is equal to twice all other numbers. Okay, no, it's not. That's not going to work for integer domain or like any useful domain, right? Like so, multiplying by 2 somehow collapses all elements into a single one. Okay, perhaps there's some algebras where this is true, right? Like, but this is not integers, and so there exists a number which is twice all others is false over integers. And once you understand this, that this inner predicate is kind of simple to evaluate. It's like basically once you understand this inner predicate, it's like obviously says something false about y, then you don't really have to worry about whether there exists a y that makes this true or for all y. They're all false, right? And in fact, once you established that this predicate is false for all, so wait. So you establish that it's false for all y, then immediately follows that it's false for that there exists a y that makes it false, right? So it's out of these two, it's this one that you should evaluate first. But of course, you know, it sort of depends on whether, you know, this happens to be that once you establish that this is false, then immediately this will be. Let's switch the orders. So we basically look at all 4 possibilities of some quantifier of y and some quantifier of x, but in this order. What about we switch the order? So what if we say there exists an x such that there exists a y such that twice x is y, or, right? So let's use the same methodology. Let's look at these two and recognize that there are predicates on x, where the predicate is this inner thing. The inner thing says about x that there exists a y such that twice of x is y. So that's my predicate here that I will recognize. The green predicate is there exists an y such that twice x is y. It's a predicate about x. Okay, that there exists a number. Now, look, once you understand that this is what it says about x, that is inner predicate, that's what it says, that there exists a y such that 2x is y. So what does it say? That x is half of some other integer. So in other words, there is some integer, like if I take twice x, I get an integer. Well, true. You can multiply every integer by 2, and you always get an integer. Over this domain, it works. Like you can, basically all this says is that an x is an integer that can be multiplied by 2, and it results in integer. Well, we all know it's true. So once you understand this, then you see that it's very easy to evaluate these quantified expressions, because this guy says there exists an x which can be multiplied by 2. Well, true, it's for all x, and right. So this is the one that you would immediately, once you understand what this inner predicate says, then you see that both of them are true, both these. How about this one? For all y, twice x is y. So it's this purple predicate. It's a predicate on x that says for all y, twice x is y. So x is somehow half of all integers, right? And that's obviously false. It is not true. This predicate is false for, in fact, any x, right? Because for every x, I can give you a counterexample. I have y that falsifies this expression. In fact, twice x is unique. So I take any number different from twice x, make it y, and it's going to falsify this. So R of x is false for all x. And so I know how to evaluate these, right? So the lesson from this is that, first of all, so you can read the sequence of quantifiers as inner thing is a predicate on the variable in front. And if you don't know how to parse this, then think of this inner predicate. What does it say? Evaluate it sort of by itself as a predicate on x. Examine what it says, and then conclude whether that predicate is true for there exists x, which makes the predicate true, there all x makes this predicate true. Okay. And once you do this procedure, then it might somehow become very simple. Another thing to notice is that it is the order is sensitive. When is it not sensitive? So the first one here and the first one here are both true. The first one here, the last for all, and the last. So this one and this one have the same value, and this one and this one have the same value. That is not a coincidence. That is always true. If you have a sequence of existential quantifiers, you can flip them in any order, and it's intuitive. When you say that there exists x, which makes something true that involves x, and what that is that there exists a y, which makes the next thing true. You will think true that if you reverse the process, it will be a different path, because the inner thing will, in one case, is a predicate about y. And if you replace it like this, then inner thing is a predicate about x. And yet they always have this same truth value. And the same for universal quantifiers. But once you have a quantification which goes from universal to existential, or the other way around, flipping them might not preserve the truth value. Okay, so this is the row which is different. Okay, I believe this is a good time, so I'm not going to go over. So I will stop recording right now.